declare the conference to be open. So I'll now pass the chair over to Professor Nellie de Beely, who's going to chair the 2020 RILEM Robert Lemaitre Medalist plenary lecture. So if Nellie takes over control of the screen, I believe we're good to go.
Okay, thank you, John. I hope you can all hear me.
I can.
You can. Okay, that's a start. So welcome everyone. I'm Nellie de Beely, professor at Ghent University in Belgium, and also the chair of the Technical Activities Committee of RILEM. And as TAC chair, it is my pleasure to introduce the Robert Lermite Medalist of this year, of 2020. So this Lermite Medal is awarded annually to a researcher under the age of 40 who has performed high-level scientific research in the field of construction materials and structures. So for the selection of the Lermite Medalist 2020, the jury had again actually a quite difficult task, since 18 very good applications were received, and there were several outstanding candidates amongst them. Finally, Tung Ling, also called Bill, was selected based on criteria such as a clear description of his research topic, evidence of research impact, leadership, international service, and prestigious awards. Bill Ling obtained a PhD from University of Technology Malaysia and did research afterwards in Hong Kong, UK, and USA. Currently, Bill Ling is a professor of civil engineering at Hunan University, China. He has focused his academic career on the study of low-embodied energy construction materials. Key pillars of his research include the carbonation of waste and cement, treatment of waste, direct recycling of non-hazardous waste, and smart materials. His research innovations have had a direct impact on the industrial application of sustainable construction materials. Professor Ling is a senior member of RILEM and is an active member of several committees related to durability, supplementary cementitious materials, as well as valorization of waste, such as the RILEM committees AAA, CCC, and WMR. Professor Ling's remarkable leadership and research independence is evidenced by the productivity of his large research team, as well as his significant international contributions. He serves on many international scientific committees and is a peer reviewer for scholarly journals, including our own Materials and Structures. He has also been the recipient of several prestigious awards. Well, unfortunately, I cannot hand over the real medal to him today, but it will be sent or given at the next in-person event, and I hope this will come soon. So I'm looking forward to hearing his medal lecture that will be given now.
Hi everyone, good morning. My name is Tung Ling, or you can call me Bill. I'm from Hunan University, China. A special thanks to RILEM for giving me this opportunity to make my presentation today. It's a real honor to receive the Robert Lemaitre Medal. For the past 15 years, I have been working on waste recycling or turning the waste into eco-environmentally friendly material. I did my PhD in waste rubble and joined Professor Poon, C.S. Poon, as a postdoc fellow at the Hong Kong Polytechnic University, dealing with a different solid waste material, including bottle glass, cataract glass, construction and demolition waste. As for the bottle glass and C&D waste, it is relatively easy to be recycled and reused in the construction industry without any special treatment. However, for the CRT glass, due to contain certain level of lead, we have developed a chemical treatment process to remove the lead before it can be safely used in concrete. And recently, my research has focused more on the use of CO2 as a green approach to activate the alkaline solid waste, and also as an enhancement method for the cement-based material. So this leads to my today's presentation topic, on the development in the active use of CO2 in waste and cement for sustainable construction products. A little bit background of mine. I spent 4 years time in Hong Kong and 2 years time at the University of Birmingham as a lecturer. Before I joined Hunan University as a professor in 2016, I was working at the Federal Highway, US, focused on the recycled glass, in particularly concerning the ASR problems. And what is the sustainability challenge that we are facing today? Concrete is by far the largest material used in the construction industry, and the demand is ever increasing, and also is predicted to increase in the coming decades, because we know that concrete is cheap and environmentally friendly as compared to other man-made material. Due to the huge amount of cement productions, so it also contributes to the 5 to 8% of global CO2 emission. So certainly, we have to confronting this challenge in the future or now. So in response to this, European Union and other countries have committed to net zero CO2 emission by limiting the global warming to 1.5 degrees C around mid of the century. So the major emitter country like US, China, or European Union should play a key role in achieving this target, or else it's very difficult to meet the net zero CO2 emission by 2050, regardless of what other countries do. So we know that we need to meet the challenge, but the question is, how can we get there? So it requires us to do two things. First is to reduce the emission close to zero as possible, and it should be happen as quickly as possible. Second is to capture the CO2 from the atmosphere as much as possible. So I take the cement production as an example. So this is a 2050 roadmap introduced by the European Cement Association for the reduction of CO2 in the cement value chain, including the clinker, cement, concrete, construction, and recarbonation, or we call it carbon capture and utilization. So the aim is reduce the current CO2 emission due to the production of cement down to zero by 2050. And we can see that for each category, they actually have contributed to a different percentage of CO2 mitigations. So the biggest mitigation potential lie in CCU. So far, the attention or developing technology for CCU is relatively limited or is still under developing, especially for the construction or concrete industry. So what is the potential for CCU in construction sector, including concrete or carbonate aggregate? So from the figure, we can see that concrete is still remain the biggest market size in now and in the future. And also the potential in CCU for concrete as represented by the size of the bullet. In the next 10 years, even they can double the potential. However, if compared to other sectors, for instance, the carbonate aggregate by 2030, this sector will surpass the concrete for the potential as CO2 mitigations. So why the carbonate aggregate show the biggest potential for carbon mitigation? So they actually predicted that if the strategy action is implemented, they can have potential to mitigate 3.6 billion tons of CO2 by 2030. So the key reason is because we have a huge amount of alkaline solid waste across different regions and the country. And this material is a very good medium for CO2 sequestrations and can convert into the carbonate product. And the whole process requires less energy input. And a brief overview of what I'm going to look into today. So the role of CO2, or what CO2 can make concrete life cycle more sustainable. So we know that CO2 is emitted from the cement plant and the amount is huge. And so we can actually utilize the CO2 for curing for the cement blocks or ready-mix concrete. And during the service life, depending on the type of application, actually CO2 can be reabsorbed back to the concrete around 5 to 20%. And the end of the service life, depending on how we recycle and handle the material, CO2 actually can take out another addition 5 to 10% of CO2 from the atmosphere into this material. So it is very important that we have to develop the CO2 utilization technology or to promote in the construction industry so that we can make our concrete more sustainable. And apart to reduce the output of the waste material, we try to consume the waste and reuse in the new concrete. And also very important is we have to find new alternative material to conserve some of the natural resources in the construction industry. So this is my focus for the presentation today, is how we can turn the alkaline solid waste coming from different industry, including mining industry, that activated with CO2, we can turn into a CO2 active binder to replace some of the cement through the wet and dry carbonation process. And also we can use a granulation, can turn the product form into the pellet and use CO2 as solidification approach to solidify and denser the microstructures. And through the compaction or the molding pressure, we can make different types of concrete blocks to replace the conventional construction products. So in my following slide, I will focus on these three main parts: the CO2 active binder, CO2 aggregate, and CO2 blocks. But at the end, before the end of my presentation, I will touch a bit about the technology developed by the carbon cube for the ready-mix concrete, and also Solidia technology for novel cement that able to absorb higher amount of CO2. So first part, the CO2 active waste binder. So in the construction industry, we know that usually we are adopting the direct carbonation approach because it is less complicated, does not involve any extraction and the use of chemical reagents. And the direct carbonation can be accomplished through the reaction with CO2, either in dry route or wet route. For the dry route, it is more straightforward and favorable for insoluble material. However, the reaction is slightly slower. But for the wet route, they can enhance the reactivity through the ion mobilizations in the reactions of carbonic acid with alkaline metals. And as illustrated in this figure, we know that the carbonation of solid alkaline waste actually have a big potential for the CO2 reduction due to the utilization of this carbonate solid waste as SCM. And one of the recent study, we are using concrete solid waste, CSW, as a CO2 active binder. So this waste is generated from the ready-mix concrete plant for the reclaiming process to recover some of the coarse aggregates. So after the process, we're able to collect the CSW, and we dry in our lab, and we found that they have contained a certain amount of fine aggregate and unhydrated and hydrated cement particles. So we running under the dry carbonation process in the CO2 chamber at RH of 65%, 20 degree, and concentration of CO2 20%. So we carry out changing the test for the maximum CO uptake by this material, and we found there is a maximum of 20% CO2 uptake at the water to solid ratio around 0.25 at 72 hours of reaction process. So based on the strength activity index, this material could be used as a new supplementary cementitious material in cement and concrete. Another study, we use a hydrated cement powder, or often we call it cement waste powder. It contributing to 30% of the waste concrete, and this material actually regarded as a very low value due to the high water absorption. So through the dry carbonation process, we found they have formation of calcite around the particles. So this in turn to increase significantly the specific surface area, and also decrease the hydrated bound water. So we use the carbonated HCP as a replacement for cement at 50%. We can find that they have a comparable or slightly higher compressive strength at 28 days if you compare to Portland cement sample. A study from a Korean researcher, they use a wet carbonation for cement waste. After the carbonation, the CSH have converted to the calcium modified silica gel, in which the calcium ions is replaced with a part of silica during the polymerization. So this also in turn to increase the absorption or the capability to absorb the heavy metal. We have compared the dry carbonation and wet carbonation for the BOFS binder. So the dry carbonation parameter is similar with what I mentioned in the previous slide. We also test the parameter for the carbonation in terms of gas flow, temperature, and the solid to liquid ratio. So we found that the optimal value is 2 liters per minute, and temperature of 40, and solid to liquid ratio at 0.3. So we are measuring the reactivity of the material by measuring the CO2 uptake. So if you can see from this figure, so under the wet carbonation at 20 minutes, actually we can achieve 9.6% for CO2 uptake, which is already more than the 0.9 recorded at 28 days under the dry carbonation. Therefore, it is very important we have to know the nature of the material that we are using, and to fix the purpose for carbonation route. And if we are aiming for higher amount of CO2 sequestration, the wet carbonation could be a very good approach. And it's also very important we have to understand the efficiency and the rate of the reaction pathway for both dry and wet carbonations. So under different conditions, it's also have different effect for different waste material. So we also have to determine the maximum limit value of the inclusion of this active binder in the cement or concrete. And they contain some of the calcite or silica gel, and what are those important roles that play in the cement matrix. So whether they could accelerate the early carbonation, or how they actually perform at the later age strength development. So the use of alkaline solid waste for carbonation is always we concern more about the leaching and the absorption for the heavy metal. So this is the second part of my presentation, CO2 granulated aggregates. And we see that they already have using the accelerated carbonation technology in 1999 for the manufacture for CO2 waste aggregate bicarbonate. So we can turn the different waste in the powder form into the pellet, okay, through the granulation and pelletization technique. And through the accelerated carbonation, we can activate and stabilize the heavy metal so that we can use for different applications in construction or other sectors. So the question arises to us is, when is the most appropriate time to inject the CO2, whether during the granulation or after the granulation? So we use a BOFS slag as a raw material to investigate the impact of CO2 injection during and after the granulations. So we apply CO2 during the granulations at the concentration of CO2 at 100% and run the granulation for 30 minutes. And after the granulation, we also can apply the CO2 or we put the aggregate in the CO2 chamber and keep the CO2 concentration at 20%, 20 degrees C, and exposure for 4 days. And after that, we have further cure under the natural air until 28 days for testing. So we have prepared 3 series of aggregates. AA is referring to no carbonation, no CO2 has been applied during the whole process of aggregate production. AC is referring to only CO2 is applied after the granulations. CC is referred to CO2 was applied during the granulation and after the granulation. So this is some test result for the 3 series of the aggregate. We found that the loose bulk density for the CC aggregate is significantly lower than the AA and AC aggregate. So we can expect they also have the higher water absorptions. And if you compare the pellet strength for the AC, which the aggregate exposure to the CO2 after the granulation, we can attain the strength more than 5 megapascal. However, for the CC aggregate exposure, we are injecting the CO2 during the granulation and also after the granulation. We found that the strength is significantly reduced, only able to have a 12% of the strength of AC aggregate. So we carry out some microstructure analysis, and based on the BSC image, we can measure the micro hardness, and through the image analysis, we calculate the porosity and also measure the CO2 uptake. As for the AA aggregate, there is a very similar for the core and the shell layer, and the lowest porosity and highest micro hardness value was found for the core layer of AC aggregate. And surprisingly, we also found that the core layer for the CC aggregate has the highest porosity. So this is also explained why we have a very low strength for the CC aggregate pellet. So the key reason is because during the granulation, we apply 100% concentration of CO2. So, and we are also using the very reactive material, BOFS, for the production process. So the aggressive carbonation reaction is taking place and release extensive heat and breaching water to create the pores. However, this situation might not be similar if we are using a low CO2 reactive material instead of BOFS slag. And for the CO2 applied after the granulation or CO2 curing, it is very beneficial for the strength development, and we can reduce the water absorption. And we're also using the granulation process to incorporate some smart material, for example, phase change material for latent heat storage. So we'll apply PCM with other raw material during the first step of granulations. So the second step of granulation, the main purpose is to make a shell layer to protect the leakage of the PCM. So we have, this is the aggregate. We can see they have a clear, obvious difference between the core and the shell layers. So we have done the test for the leakage test, and the result is promising. Also, we have carried out the thermal properties and as incorporated the PCM aggregate in the concrete panel and exposure to the indoor and outdoor conditions. And we found that we recorded 1 degree C lower for the aggregate PCM aggregate panel. So reflecting that they have a better thermal performance and also potential for energy saving. And we're also interested to see the aggregate will produce the when we incorporate it in the concrete. So we replace 100% of the cost aggregate of natural from natural and also from the commercial lightweight aggregates. And we can maintain the strength at 28 days, 30 megapascal. However, if you can see for the commercial lightweight aggregate, it only can attain 10 megapascal. And if you compare the compressive strength with the fracture strength, the reduction for the fracture strength is much lower. And we are expecting the aggregate we produce will have a better bonding between the aggregate and new cement paste to compensate the low strength of the aggregate. So we can see there is obvious 2 different regions for the natural aggregate concrete. However, for the aggregate we produce, the shear layer might have some reactive material, including the calcite. They could have a further reaction with a new cement to improve the bonding between the layers. So this is also proved by the micro hardness result. So a bit of the applications. So the process is relatively easy, simple, and technically feasible as compared to the CO2 active binders. So we also can design different property. We can make the aggregate lighter and have a functional property. We can incorporate the PCM, and the process we can have to maximize the use of waste. So this is very good approach to apply in different countries, because at different country, different region, different area, they might have a different waste material. So we can consume a lot of waste material and as a medium to absorb the CO2. So this could be a very potential promising approach for carbon sequestration strategy. And also we can establish a green supply chain for the construction industry. And the part of my presentation, CO2 block. So CO2 curing actually has been researched since 1960. So certainly this is not a new technology. And it's very interesting. The block has a very high potential for carbon sink. Why? So first, we know that concrete block is prepared with relatively low water to cement ratio, so that we can compact and have instant demolding feature. And at the same time, we have a higher porous structure. And during this situation, we still able to provide a sufficient moisture. And instant demolding, we have a fresh mix for concrete or alkaline solid waste material. And before the harden, we have an open pore structure, which have a high permeability for the CO2 gas diffusion. So this could be almost the very ideal condition for CO2 reactions. And we also can incorporate different kind of CO2 active material. For instance, steel slag as the binder to make the concrete block with a very high strength. And we know that a part of the raw material, the key influence parameter that affecting the performance for concrete block is the compaction or molding pressure or the liquid to solid ratio, because the compaction will influence the packing density and availability of the pore for carbonation. So the liquid saturation also influence the diffusion of the CO2 and for the carbonations. So in our study, we have studied the different parameter, liquid to solid ratio, the molding pressure, and also the carbonation duration. So from this figure, as we can see, if we are decreasing the water to solid ratio and decreasing the compaction pressure or molding pressure, we in turn to increase the initial air void, okay, 13, 19, 26, okay, represented by the dotted line. And this will also help for the CO2 diffusion. However, at the very low water content, it could limit the CO2 reactions. So the best water to solid ratio is around 0.13. And doesn't necessarily that we found that the highest CO2 uptake will have the highest compressive strength. So we can see the compressive strength achieved at the highest molding pressure, but also is somewhere around 0.125 or 0.13 water to solid ratio. As we can see at this region, we also could have quite high CO2 reactions or CO2 uptake. So the preconditioning is very important parameter that we have to consider whether we need to remove some of the excessive water before we run the CO2 curing. So we have selected 4 different samples with different water to solid ratio, and we found that this is preconditioning, this is non-preconditioning. So we're preconditioning for 2 hours at 20 degrees C with RH of 50%. So we found that after the preconditioning, actually for the low water to solid ratio, that decrease the reactivity, CO2 uptake, as well as the strength. However, for the high water to solid ratio, the preconditioning actually could help to increase 20% of the strength. So we can conclude that if we have an optimum water to solid ratio, we can extend the preconditioning. So we also did some kinetic reaction kinetics through the shrinkage core model. And we have calculated the effective CO2 diffusion rate. For this, the lowest molding pressure and the lowest water to solid ratio, we found that the diffusion rate is 8.16. If you compare to the high molding pressure and high water to solid ratio, it is almost 30 times lower than this sample. And we're also using the QSRD to quantify the phases, and we will see the evolution with different CO2 uptake. For the sample 1 is referring to the lowest CO2 reactivity. The sample 5 is referred to the highest CO2 reactivity. As we can see, there is a reduction of pollen-type and both sides if we increase the CO2 reactivity. And increase the CO2 reactivity, also we found that the calcite, magnesium, and amorphous phases has been increased. So as for the CO2 cement plot, we also have investigated the compaction pressure and water to solid ratio. And this is also without preconditioning. We have tested the effect of 2-hour early carbonations for different samples. So 2-hour carbonation is referred to the first column. We can see there is no effect for the under the low molding pressure if we are changing the water to solid ratio. However, as for the high molding pressure, if we increase the water to solid ratio, there is a decreased trend for the strength, especially when we achieve the high water to solid ratio 0.175. At this situation, we could have liquid to blocking the CO2 diffusion. However, if we Further curing with water until 1 and 7 days, we see there is a not significant difference for the different water to solid ratio. But as we increase the molding pressure and increase the water to solid ratio, we will in turn to increase the compressive strength of the sample. We also test the different layers for the TG to calculate the calcite content and to measure the pH value. And we found there is a good correlations. And for the CO2 concentration, as we increase the CO2 concentration, actually based on the result, we found that it could help for the cement hydrations and also for the CO2 reactions. And as the cement block, CO2 cement block could be a new potential building material, so the risk to expose to the fire could be increased. So additionally, we know that the microstructure or reaction products of CO2 block is totally different from the sample with a conventional natural air curing. So we are exposure to different high temperature, 200, 400, 600, 800, and we found that the residue compressive strength up to 600 for CO2 curing is still remain relatively high and able to maintain or to keep the calcite content until 600. But further increase the strength, increase the temperature will significantly reduce the strength as well. So we know that the CO2 curing is kind of beneficial for the high temperature property for cement block, at least up to 600 degrees. And the applications, so again, this is also technically feasible and low barrier because we can set up easily the curing chamber in the conventional cement concrete plant. And we have no concern for the steel pollution. And also, we have a few performance standard requirements as compared to structural material. And very interestingly, based on the literature, we found that there is a wide range of percentage for the CO2 sequestration for different type of block. So different type of block, solid block, hollow block, the size effect, and different material, different compactness, different liquid to solid ratio will really affect the amount of CO2 sequestration. And also for the future, we have to find a more economical and environmentally friendly CO2, maybe sourced directly from the flue gas or the landfill gas. So one slide for the CO2 ready-mix concrete. So this technology actually has been developed by the carbon cure technology, simple retrofit process, and it can use existing production equipment. So CO2 is injected into the concrete truck, and once the cement mixing with water, it can dissolve and release the calcium ion to react with CO2 to form the nano calcite. And we found that the result found that they can use 5% less cement under the CO2 curing. It could also provide a 12% higher strength than the control sample. They mentioned the durability is generally remain unchanged, and however, the workability is a little bit less than the conventional concrete. So the plant is already applied over 100 conventional ready-mix concrete plant across the US and Canada. So they can reduce 80% of kg of CO2 for 1 ton of cubic meter of concrete using this technology. CO2 active material. So this also has been pointed out in 1979, CO2 to harden the cement. And by the solitaire technology, they have manufactured this novel cement using low calcium oxide. And in turn, they can reduce the sintering temperature down to 1200 and also reduce the CO2 emission by 30%. So they use the CO2 to cure the cement instead of water for the hydration, so able to absorb 250 to 300 kg of CO2 for 1 ton of cement. And the reaction, we can see after the carbonation, they form the calcite and silica gel to build up the pore. And the microstructure look more denser than conventional concrete. And the strength at 24 hours is comparable to the 28 days conventional concrete. And the major concern is the low pH value. Is lower than 10, so they have a potential risk for the corrosion. As I know, they already work on this together with the Lafarge cement company to really make this application wider and solve these different challenges. To summarize, and the key focus for the concrete life cycle to meet the net zero CO2 emissions, I think we have to pay more attention to the recarbonation or the utilization of CO2 during the life cycles. And we have to find a more economical source for the CO2. And we need to do more tests to ensure the durability performance. And apart for the output of the waste, we need to make the concrete life cycle more sustainable. We have to find more alternative input material. So there is a huge opportunity because we have a huge amount of alkaline residue from different industry. So the technology, as I mentioned in the previous slide, is relatively low compared to other sectors, especially the technology for the granulation and the compactions. But we're still having the challenge for the economical aspect and the safety because they have a competitive price in the construction market. And we have to find a more simple process. And also there is a concern of the heavy metal because different kind of alkaline solid waste. And more importantly, the supply chain is so important because we need to ensure the quality and quantity that we can solve for the productions. And of course, the regulatory specification, we need to work together actively with the policymaker industry so that we can mitigate the challenge, especially for the specifications and regulatory. And we need to get support from different industry. And to end, I would like to thank many people, especially my team member, my student, my postdoc, and also Professor C.S. Poon for leading me throughout different my career academic, and also my friend, my collaborator from Malaysia, Dr. Mo and Dr. Pang from Taiwan, and my friend from mainland China. So if you happen to visit China, please come to visit Changsha or Hunan University. So you can do 3 things. Apart from the academic discussion, actually we can do hiking. So this is the picture I took from the Yellow Mountain in our campus. So you can do the hiking, and also you can visit our Yellow Academy, which have 1,000 years of history. Okay, so thank you very much. If you have more interest.
Okay, thank you. I think the presentation was finished a little bit abruptly, but we have Professor Bill Ling with us for answering some questions. So I've seen that many questions already came up in the chat.
Yep.
So well, the organizer, since this is the first session, will have to help me a little bit how to handle this best. I assume I can just read myself the most interesting questions. Sometimes several attendants have asked similar questions. So
yes, please do.
Yeah.
And for those whose questions don't get answered, we have, and there are information in the conference documentation of how to access the networking spaces. If the presenters can hang around in the networking spaces on a few occasions during the week, if you bump into somebody in those spaces, you can ask additional questions at that point as well.
Okay.
Okay, great. So we have a few minutes, I think, for taking some questions. Let's start with the first questions that are dealing with the actual waste materials that are recycled by this CO2 injection or treatment. And if they are all widely enough available, like for instance, there was a remark that the BOFS is maybe available in only a small amount compared to the amounts of CO2 that are produced by the cement clinker production.
Okay, so thank you very much. And so the waste we are trying to use is mainly coming from the different sort of waste that from the mining waste or different industry. So actually, if taking the BOFS as an example, of course, it is not enough for the sequestration from that generated by the cement plant, as pointed by Karen. But we are trying to use a more value waste material, which sometimes they could have a very low reactivity. So we have a different purpose depending on what is the target, because some of the low reactive material we still can able to activate using the CO2, but we aim for a low value applications. So all this waste we are not really regarded, the original waste is not regarded as a SCM, but after we active with the CO2, we found that it could be a partial replacement, at least for 10–15% in some situation to replace the cement. So I'm not sure whether it's appropriate word after the carbonations. We can call it as a SCM, or we call it as a CO2 active binder. So yeah.
Okay, thank you. So it's clear you're not using the generally used SCMs, but lower value wastes, I take
Yes.
that. Yeah.
Yes.
There was also a question regarding the granulated aggregates. If their crushing resistance is sufficient for then afterwards using them in concrete, the aggregates stay in one piece, they get not further fractured?
Okay, so this also depending of what the application that we are going to produce. For instance, if we are making the block, we also have a concern of the compactions, because in the plant we're also having a high compaction during the whole production process for the blocks, as well as for the mixing in the concrete. So far, that aggregate we produce with the cement waste powder, we're able to achieve 2 to 3 megapascal. So we found that they have putting into the normal conventional vibrator concrete. So we actually, for that study, we apply 100% as a replacement for the coarse aggregate. So we find that there's still like 30% of strength reductions to maintain like 30 megapascal. So we haven't see into very detail of how they fail under the different fractions. But we could find in terms of microstructure, they have enhancement in terms of ITZ, because we need to have a further study, but at least we found that from the initial result, there is an enhancement between the ITZ by reducing the width of the ITZ, and also we have see some changes in the micro hardness as well as the chemical change.
Okay, thank you. There were also some questions that all relate to the source of the CO2 and the problem of storing the CO2, like for instance, in your studies, did you only use technical CO2 or also flue gases? How should the CO2 be stored? How should it be brought to the site of use?
Oh, yeah, this is interesting. We actually, because I just recently worked on this topic like for the past 4 years. So we mainly in our lab, we use industrial CO2. So we haven't really tried the flue gas. But but now we are trying to synthesize the different percentage of to simulate the actual flue gas, because we know that the actual flue gas actually have the different gases. So for example, sulfur or NOx. So they might have a significant, or we are not sure that how much they will influence the carbonation or other cement hydration process. So we try to simulate the gases, and we are running the test, but we haven't got the detailed result. But I think some of the applications in they already are some kind of trying to apply using different kind of flue gas. But for us in our lab, we are still using the industrial gas.
Okay. And maybe regarding the concentration and other effects like the temperature, you mostly worked with 20% CO2. Did you study also effect of higher concentrations and maybe effect of the temperature on this carbonation efficiency?
Yes, because in China we are using the standard of like the accelerated carbonation is by 20%. So we also did a different concentration from 0 to 1%, 3%, up to 20%. So we will see the enhancement during the reactions. But after the 20%, they have not very significant difference between like if you go higher concentration. So in many studies, they also pointed out that because some of the flue gas from the industry, they might have less than 20, but around 20 something is good enough in terms of CO2 concentration. But we really have to look into what other gases within the flue gas had the impact on the cement hydration, because this is a very complicated process, because we know that the hydration is already complicated in the cement matrix. But now we are applying the CO2, and CO2 is diffusion control, and many complex chemistry or reactions is taking place in that system. So I think it's very worth that we will have to look into more detail if we are applying the flue gas and different from the different sources of the gases into the concrete for the carbonations.
Okay, maybe very quickly about the effect of temperature. Did you study that?
We haven't go for very high. We have tried for the aqueous, the wet carbonation. So they have an optimum value for the carbonations reactions. But for the dry carbonations, like under the ambient, we usually under the ambient temperature. So so far we didn't test much for the different temperature for dry carbonations.
Okay.
Yeah.
Thank you.
Yeah.
Well, there were many other questions also in the chat, but maybe
I will try to answer
later, because I think we are already using up 5 minutes of the next plenary lecture, so we do not want to run too much over time. So thank you again for this very interesting lecture. I hope that the other attendants having questions can address you later or maybe send you a mail. And I hope also to be able to hand over the RILEM medal on another occasion. So
okay, I just see the message from. Can I turn the video? So sorry. Yep. So thank you.
Thanks again. Yeah, I will hand over the chair to the local people in Sheffield.
This is me again. So thank you very much to Nelly and for the continuing the annual tradition of excellent RILEM Medalist lectures. And we're very pleased to have been able to open the conference in this way.